Okay, so we have introduced the closure attributes and the closure FDs, and we also provide you with some examples and algorithms to calculate the closures as well. And we also provide you with some examples about how to use the closure FDs and the closure attributes to help us decide the keys of the relations. And you may wonder, why do we need to study the FDs and the keys together? The main reason is because key is also a special type of FD, right? According to our previous knowledge, we know that based on the keys, we can derive or we can imply all the attributes inside the relation. And in other words, given the key of the relation, we can derive a FD, right? For example, if we have a relation about the students in the FSU with FSU ID, name, age, and department, then we can derive a special FD, right? Because we know the FSU ID is a key. According to the definition of key, we know FSU ID can imply name, age, and department is these attributes, right, in the relation. So keys are a special FD, and they can also be very useful. Normally, given a relation, we prefer very good FDs, like the keys. If we have a FD and then the left-hand side is a key, then we can say this FD is very good for the relation. And besides these kinds of FDs, we can also have some other FDs. If the left-hand side are not a key of the relation, then we can say they are very bad FDs, right? So we have the good FDs versus bad FDs. And we can provide you with another example. Now for the students in FSU, now we have FSU ID, name, as well as department and department chair. If we have a relation like this, we can derive different FDs, right? We know we have FSU ID implies name, department, and chair, these kind of attributes. This FD is very good because the left-hand side is the FSU ID. It is a key for the relation, right? And we can also have some other FDs based on the attributes. We also know that department implies chair. According to the semantics of this relation, we know that given a department, we can find one single chair, right, in a department. Therefore, department implies chair is also a valid FD in the relation. However, we say this FD is very bad because the left-hand side of the FD is not a key for the relation, right? So therefore, if we have such FDs in the relation and left-hand side is not a key, then in this relation we have some problems. Because we have a attribute which can actually imply some other attributes while we organize them together in the same relation. We can easily divide this relation into two, right, to avoid redundancy, right? Now here we store the CS and Xin Yuan, right, twice in the table. We can actually remove this kind of chair information from the table, right, to another table instead. In this way, we can avoid storing the same information again and over again. So therefore, from the FDs and the keys, we can find some redundancy in problems in some relations. That's the reason we need to have some normal forms to help us to further polish the relation like this into better ones. We will show you how to derive the better relations by using these normal forms in the next week. So you need to know, based on the FDs and the keys, we can find some redundancy problems with some relations, and based on them, we can further introduce normal forms to help us. So this is a lecture to be provided in this week. I hope you can follow me, right? We have so many examples, we have so many algorithms introduced, and we have different concepts. So do please go over all the examples and also do the examples by yourself first and check the answers again to make sure you can follow the materials we have provided. And besides these lectures, I also have to take-home exercises for you, right? I need to clarify they are not the quizzes. They are just some exercises prepared for you. I have 2 questions prepared for you. So you can do this by yourself and also get your answer, right? So let's assume we have 2 problems. The first problem is given a relation R. R covers what? R is a relation. It covers multiple attributes. E, F, G, H, I, J, K, L, M, N. And we have a bunch of FDs. We have FD set. S equals to what? S equals to EF implies G, F implies IJ, and so this EF being means given two attributes EF, it implies G, right? This means F implies two attributes I and J. And the next one will be E, H implies KL, and K implies M, L implies N. Let me check this FDs. EF implies G, F implies IJ, EH implies KL, K implies M, L implies N. Then the question is, which is the key of the relation? We have different options for you. Let me change this number. The first option is EF. Second one is EFH. Third one is EFH, KL, and last one is E. And you can do this exercise by yourself and get your answer. So we will not be able to do this together because the time is limited. Besides this, we have another exercise question. The question is like this: given a relation R, it covers multiple attributes A, B, C, D, E, and we have FD set S equals to A implies B, A implies C, CD implies E, B implies D, E implies A. Let me check this FDs. A implies B, C implies CD implies E, B implies D. Okay. Then the question is, which of the following FDs is not implied by the above FDs in set S? We will provide you with different options, and you may need to get the answer by yourself. Let me copy this one. The first option we can get is CD implies AC. Second one is BD implies CD. Third one is BC implies CD. And last one is AC implies BC. And you can try to do these two exercises by yourself and get your answer. And we have no time to go over these two exercise questions for you in the lectures. Okay, so that's it for this week lectures, and I hope you have a nice weekend.